Okay, guys, let's do some more FEA. Okay, for now, we have gone through enough examples and lecture and on rod and truss elements. Now, I just posed another set of homework for you guys. If you have no problem for today's lectures or examples, you should have no problem with that new assignment. So good luck to you. I would say you need about half an hour to do that problem set, but I'm very generous. The due date is on next Friday midnight. Do not wait till the last minute. FEA is funny. It takes a lot of practice. The more you work on it, the better you are. And also, please pay attention to details. Even like what I did, in my examples, I switched notes 2 and notes 3, and it totally confused me. So just make it simple, make it straightforward, then you'll be fine. Okay, let's do some more work on finite elements. Okay, minimum potential energies. Okay, now I'm going to show you, let's say I want to invent a new element. What is my approach? Okay, and let's say assume I do not know anything about rod elements, and I want to develop the stiffness matrix for the rod elements. Let's see how it's done. Okay, I want to define a 1D element. Okay, has 2 nodes. So it has a reference frame X and Y. Oh, but you know what? Y doesn't matter because it's not going there anyways. So it has a rod. Okay, on one node, has force acting on it, and it's allowed to move U1X. Okay, by the way, this is node 1, and this is node 2, and it's allowed to move 2, and then F2. Nothing fancy. Okay, just like what we did before. Total length of that thing is L. Okay. We know node 1, the displacement is U1. Okay. And node 2, we know the displacement, well, because we only have X right here. Only one, we don't have to write X anymore because there's no Y movement. But what about something in between? What about this node? What's the movement in between? We do not know, so we have to assume something. We assume the movement is a function of X. And it has 2 constants. Okay. So everything is as a function of X. And we have 2 constants. Okay, let's solve for those constants. Okay? Now, when X is equal to 0, okay, when X is equal to 0, our displacement is U1. When X is equal to L, our displacement is U2. We convert everything into matrix form. Okay. We inverse that. Okay, you get this. The inverse of this 2 by 2 matrix is like we sub everything. We sub everything back to equation 1. Okay. So u x we leave this term alone and we only multiply these two terms. You get we just introduced a new term. This term is called shape function. Now, shape function is very, very important in order to develop a new element. That's the first step. Look what, so what does shape function tell me? Try it out. If you apply, if let's say x equals 0, okay, what do you have? 1 minus 0, u1, u2. Guess what? You have multiplied together, you got u1. Any questions so far? Anything in the chat box? Nothing?
So were you substituting that back into that what formula again? Which one? Equation 1? Can you go up for a sec?
Oh yeah, it's right here.
Onto the initial subfunction at x. Okay.
You see it? C1, C2, right? So I solve for C1, C2. This term is right here. And C1, C2 is right this term.
Okay.
Is that good? Okay. Now, let's put shape function on the side for now. Let's look at the energy or the energy stored within the elements. Okay. Okay. I have a rod. A force is applied to it, and there's an X movement. X is a displacement, okay? And this is a uniform area. Okay, right here, the total length is dx. The area is dy and dz. Somehow it's reversed, right here, x is the delta, but the total length of this element is delta x, is dx. Okay, so the string energy within that element is the work done along the x. Dy is the total length. And x is the displacement. But we know F is a kx. We take the integration of that, it turns to but because k is equal to E A over L. Okay. And in this case, we have E dx is the total length of the element, and dA is the cross section of the element. Okay. According to definitions, okay, the elasticity is a stress over strain. So therefore, but since the strain is the delta, the displacement over the total length. Okay, I want to recall that total length is dx. The displacement is x. Okay. We move this term to the side. Let's put these things all together to here. Half dy dz dx. Okay, it's all substitutes, right? This is the elasticity. This is A over L, and this is x squared. So I rewrite the terms. And that is the volume. Total volume of the elements. Now, this is only one element, right? What about all the energy stored within the system? Then you take the integration of the whole thing. Now, so basically, all the elements If you want to invent any new elements, everything starts from this equation.
Professor,
Yes, what's up?
sorry, so what does the upside down V stand for?
Didn't I define that? Oh, I'm sorry. Okay. Energy stored in an element.
Okay,
Right
thank you.
here is an energy stored within the system. The system. And the system has many elements in it, right? Okay, let's move on. Okay.
Chris, is there a name for this symbol, the upside down V?
I forgot what is this called. You know what? I'll tell you next week. I use it all the time. I forgot how to say it. It's a Greek symbol. Okay.
Yeah, no worries.
I guess we only have 26 alphabets, 26 letters. You know, it's not enough to define all the mathematics formulas. Right? So we use funny symbol like that. Okay, keep in mind, we have a constant area, right? It's constant. It's, so okay, sub back everything. Okay, E equal to stress over, right? So stress equal to strain. Put it right here. Okay. Bingo. Total strain energy. But however, that thing is not constant. According to what we developed before, it is a matrix. Where because we define the first step, we don't want to assume a constant displacement. Everything is a function of a x. Okay. So what do we have here? Yeah, it's right here.
Is that an A beside that E squared? Or is that
Yeah.
a V? Oh, okay, okay. The area.
Where are we? Yeah, which is A. Okay. It's the state shape function. U2. Okay, take the derivative of the shape function we just defined not too long ago. Okay, one is we have -1 over L and 1 over L. We just create another very important term. String displacement matrix. So far, we have invented two new terms, the shape function, right here, and the derivative of the shape function is a string displacement matrix.
Chris,
Hey,
are
what's up?
are they both standard for an element with the constant area, or they can be different depending on the shape?
They are both standard for the rod elements with two nodes only. If you have some other weird element, okay, you will learn that in the future. For next class, I'm going to show you a beam element. It has a totally different shape function and strain displacement matrix. Okay, every type of element has their own unique shape function and strain displacement matrix. Okay, let's sub this back to here. Abs strain is the strain displacement matrix times displacement vector. Okay, the square of that thing will be d u d u. Now, be careful because it's a matrix, okay? You cannot just times them together. Okay, this is the matrix product rule, okay? Now we put everything back to that funny looking equations, okay? Upside down triangle, okay? Okay, it's a total string energy. Okay. At one point, okay, when the total potential energy, okay, hang on, the total potential energy is all the strain energy stored within the work done. When I'm pressing or pulling, the strain energy within it but outside is work done on it. Okay. During the equilibrium position, when you take derivative of it, when everything is in steady state, nothing's moving, during the equilibrium position when nothing is moving. Work done equal to when everything's in equilibrium, okay, the stored energy is equal to work done. I want to calculate this term, right? So I take the derivative of this whole mess right here. So what I have is EA is a constant. I take the derivative in terms of U. So right here is a U squared. So U becomes D T D. And with respect to X, and then we take the integration of the whole mess, okay? We substitute L into the X. We have oh my God. After 2 pages of notes, guess what? I get this matrix that we use all the time in the raw elements. Any questions so far?
So will we be asked in the exam to derive the equations of the slope function and the strain matrix?
I haven't decided yet. Maybe, maybe not. But what I'm telling you is, let's say you want to develop a new element. That's the approach you make. First of all, you define the shape function. First of all, you define the shape function. Well, where is it? Shape function. And then you put everything into a store energy within the system. Oh, before before you do that, you need to define the strain displacement matrix, which is a derivative of the shape function. Yeah, it's right here. And then you use the product rules and find out the stiffness matrix. In this case, right here. Now, this is only the left side of the equation. What about the work done? Remember, we have to do the work done right here.
So, sir, what is that equation called on the bottom?
This one?
Yeah, the one that you just finished.
This one is the total strain energy stored within a system. Cool. It's a mess up.
Professor, just a quick question.
What is it?
The matrix, the x over L squared, the second line, the first one, is it supposed to be negative L over x, negative x over L squared, or just negative x over L?
Sorry, I missed that. You're right. Good point. Okay, what about the work done? The work done on a system is okay, in this case, F is a function of X as well. Because right here, nothing is constant. F is also a function of X. It varies along the rod. Both is a function of X. Okay. And remember, this can be expressed in a shape function. So we take the derivative of the work done. Bingo. Because the U term is gone. This is gone after you took the derivative of it. So let's do example. I have a rod and I have 3 nodes. Okay, somehow the force applied to it is not a constant force. It varies along the rod. Remember in the first class, right? I only have a point load. This is point load, right? But now it's not. It has a very unusual force. Change along the length of it. Okay. And the total length is 20 inch. Each element is 10 inch. And of course, we name them 1, 2, 3. The cross-section area is 1 inch square. Okay. We want to find out the deflection on notes 2 and 3. Okay. Okay. The K value will be EA over L for all rod elements times 1 divided by L, which is 100. Okay, let's look at the force. The force will be integration of what is the shape function for rod element? One minus x over 10, and then x over 10. We take the derivative of that. We put 10 outside, take the derivative of that, it will be x. Sorry, I didn't say derivative, it's integration. We put in, substitute 10 minus 0 of it will be 5 and 5. 50, 50. This is only the first portion of it. Let's do this second one. F2. Same integration, but instead it is jumping from 20 to 10. Okay. Twenty minus 20 minus 10 minus 5. 20 squared divided by 20, which is 20 minus 5. Here we have 150. Okay. Okay, watch out. We have a 2 force factor. That one looks after note 1 and 2. And this one looks after 2 and 3. Okay, I'm very excited. Let's move them together. Okay. It is a free note, so it's a 3 by 3 matrix. What is our K there? The K is 100, right? So each element is 100. If both sides both elements have a constant K, you can move it outside. Okay, has a displacement vector. Now, instead of a point load, what do we have now? We have two force vector. This is from here, and this one is from there. So minus 50 plus 152. That's all the applied force. Instead of one point load, we have an applied force of two vectors. And what else? Remember, we have something attached to the wall, right? So that's a reaction force. We don't know the sign, so we just say. Okay, on the right side, we have to apply the boundary condition. We know U1 is attached to the wall with 0. You put out everything together and solve for it. We got U2 equal to 1.5 inches and U3 equal to 3 inches. That makes sense, totally makes sense, because U3 will deflect more than U2 because it's at the tip of it, right? And to check everything's all right, you put the values back to the equation. You get R1 equal to negative 200 pounds. That makes sense as well, because it's 10 pounds per inch, right? And the total length of the elements of the rod, two elements, right, is 20. 20 times 10, you get 200 pounds to the right. So you got a reaction force.
So why are we adding the reaction force to the first one? Is it because we know there's a reaction on that
Yes,
rod element?
because if you don't add it there, the whole thing's gonna fly to the right.
Yeah, that makes sense. Okay.
Yeah. That's it for today. That's all I want to show you for today. So just to recap, today we did more examples on rod and truss elements. Okay, and then you have homework, a new homework on truss elements. And then I show you something new, which is the minimum potential energy, how to develop a new matrix. How to develop a new element. Okay, and try to review that. If you don't understand it totally, it's totally normal, because you guess what? This lecture alone, right? This topic alone is one PhD lesson. Basically one PhD. Like long time ago, some smart guys develop it for us. It took them 4 to 5 years to develop this, and we just use it. And finally, we went through an example how to resolve some problem by the mean potential energy example. Okay. So again, today's homework will be just to review the notes on mean potential energies, review examples, and work on the truss elements assignment. It worth 2.5% of total score. So do you have any more questions before we end the meetings?
Great. Are we gonna see the solutions for the quizzes? Like, will you post the solutions or?
I will probably go over that in a class instead of posting it. But if you want, I can go over it in the class and then send you this one note.
Okay, yeah, I just
Yeah,
want
would
to
that
make
help?
sure. I
Yeah.
just want to make sure I'd see where I went wrong or where I got things right.
Okay. I will review all quizzes before the midterm exam. Okay, so it's kind of helping you guys to study. But I'm not going to go through that too soon because I'm not all people have hand in their quizzes yet.
Okay, thank you.
Okay.
Sir, I just had a quick question on this potential energy example. Where did you get the x minus the 10x 1 minus x over 10 and x over 10? I don't see that. Right
That's the
after you
shape.
do, right after you give the equation of the f1, for example.
That's the shape function.
Okay.
Okay. Shape function 1 minus x over L and x over L. I have
Okay.
that in the first page of the note.
Yeah, thank you.
So again, every element, different type of elements have different type of shape function and strain displacement matrix. You will learn more shape function in the future, but today is the simplest one. For the raw elements, you have shape function, which is 1 minus x over L and x over L. Okay, thank you once
So,
again.
sorry, can we, I completely forgot about handing in the quiz yesterday, so can we still hand it in and get, like, obviously probably a deduction in marks, but can we still get it marked at least?
Yeah, the mailbox, the box is still open. Yeah.
Okay,
I'm
thanks.
I'm kind of flexible with the quizzes and the lab, but except the midterm exam and the final
Yeah,
exam,
yeah.
you must hand it in time. Okay.
Of course.
For the quiz, if you're late, there will be a small penalty, but not enough to kill you.
Okay,
Yeah. But I still encourage you to hand in your lab, your quiz in time.
yeah, of course.
For this course, once we get into like the lab portion of it, when we're using that software, like what is like kind of the makeup on the course, and where do students kind of like make and break their marks? Like, do they usually get burned in the beginning part here, or how does it usually go historically?
You mean the class average?
Yeah, but also like where the majority of the marks are coming from. Like students typically do better or worse in this section, and so on.
Well, in total, our theory, I call that theory, right? Or the calculation theory work about 70% of the total score, and the answers, the lab is only 30%. Okay. I don't want to put it too heavy there because some students do not have PC or Windows, right? And because it's all distant learning, we don't have a lab open for you guys. Right?
Chris, so for those who don't have Windows PC, can they share it with the friends?
Yes, you may. I encourage you to do so because seriously, Answers is a very useful tool. If you know that and if you learn that and put it in a resume, you can get a job in FEA easily. Yeah.
I mean, how would that go? So it's going to be the same project and two different reports if two guys are doing it together, right?
You know what? For this week and next week, let's still focus on theory work. I will have a special section on answers in future, and we'll go through all the rules, the regulations, and guidelines. But in the meantime, try to get a used laptop. It doesn't have to be a fancy one, you know. with windows on it, so we can try. I really want you to try answers, because we can only do by hands calculation maximum 2 to 3 elements. Okay, but if you have answers, you can do some calculations with a 4,000 elements. Very powerful. Okay, we will talk about answers in the future, but for now, I want you to understand spring elements, truss elements, and also minimum potential energy. All right, so if you have any questions, send me an email. I'll try to respond ASAP. And thank you once again for attending my lesson, and wish you all have a good weekend. Goodbye for now.